Hello, fellow denizens of the deep. Today we're going to section 11.7. Let me just share my screen. 11.7, which is isomorphisms. Now you've all heard Shakespeare said, "A rose by any other name smells just as sweet." Well, this is basically a rose by any other name. In other words, you have two things which are two different names or two different things, but they're kind of the same thing. What do I mean by that? So two algebraic systems are isomorphic if there exists a translation rule between them so that any true statement in one system can be translated to a true statement in the other. So just like a language, there's this Greek word corresponds to the word three. This is the word plus, that's the word four, that's the word equals, that's the word seven. So this, I don't know how to pronounce this in Greek, is the same as saying 3 plus 4 equals 7. That's kind of an isomorphism between the Greek language and the English language. This is a very rough, example. But let's look at something which you guys, a lot of you people I know are computer people, so you may relate to this a little bit as next thing, this next example. So we want to look at two different systems. So one system is the system of the power set of 1, 2, 3, 4, 5. Now, power set, just to remind you, power set means the set of all subsets of 1, 2, 3, 4, 5. And if you recall, there are 32 such subsets, including the empty set and the set 1, 2, 3, 4, 5 itself. Anyway, with the operation between these subsets is going to be the operation of union. So we could discuss other operations, but just to keep it simple, we're going to discuss now just unions. Now that's our first system, and we want to show that it's isomorphic to a different system, a completely different system, which is system 2, which is strings of 5 bits of computer memory with an OR gate. Now, individual bit values are either 0 or 1, so the elements of this system can be visualized as sequences of 5 zeros and 1s. An OR gate is a small piece of computer hardware that accepts 2 bit values at any one time and outputs either a 0 or a 1, depending on the inputs. The output of an OR gate is 1, except when the 2 bit values that it accepts are both 0, in which case the output is 0. Now, a lot of you people who are computer people know this already, and it's very simple and basic what I'm saying. I'm let's just bear with me. So but there may be some of you who are not computer people, and let's look at this. Anyway, the operation on this system actually consists of sequentially inputting the values of 2 bit strings into an OR gate. And the result will be a new string of 5 zeros and 1s. And now an alternate method of operating in this system is to use 5 OR gates and to input corresponding pairs of bits from the input strings into the gates concurrently. So again, system 1, we have the power set of 1, 2, 3, 4, 5 with the union operation, and there we go. And we're over here. System 2, we have strings of 5 bits with an OR, and there you go. Now 1, 2 is the same, by the way, as 1, 1, 0, 0, 0. Because I'm saying I have the 1, I have the 2, those are my 2 1s, and I don't have a 3, 4, 5, those are my 3 zeros. You get it? You see what I'm saying here? Now, if you don't get it, let's hopefully you'll get it when I explain it a little bit more. So the isomorphism. Since each system has only one operation, it's clear that union and the OR gate translate into one another. The translation between sets and bit strings is easiest to describe by showing how to construct a constructive set from a bit string. If A1, A2, A3, A4, A5 is a bit string, so these A's are all 1s and 0s, then the set that it translates to contains the number k if and only if ak equals 1. So for example, 1, 0, 0, 0, 0, 1 would be the set 1, 5, meaning I have a 1. I have zeros here, so I don't have a 2, I don't have a 3, and I don't have a 4, but I do have a 5. So 1, 0, 0, 0, 1 translates to 1, 5. And the set 1, 2 would be 1, 1, 0, 0, 0, which is I have a 1, I have a 2, but I don't have a 3, 4, or a 5. That's where they get zeros here. So imagine your computer is like a child who knows English and must do a Greek problem. To execute a program that has code that includes the set expression 1, 2, union 1, 5, it will follow the same procedure as the child to obtain the result. So 1, 2, union 1, 5, that's equal to 1, 2, 5, which is saying that 1, 1, 0, 0, 0 or 1, 0, 0, 0, 1 is equal to 1, 1, 0, 0, 1. In other words, for each position, if there's at least 1 in that position, there's a 1 at the end. So the first position has a 1 right here. The second position has a 1 right here. Now the third and fourth positions have zeros here, and they have zeros here. So those are zeros. So zeros combined with zeros give me zeros in the outcome. And the fifth position has a 0 over here, but it has a 1 over there, which is why I have a 1 in the outcome. That's how the OR gate works. But notice that 1, 1, 0, 0, 1 corresponds to 1, 2, 5. Because I have a 1, I have a 2, I don't have a 3 or a 4, but I have a 5. And that, my friend, is the story. That is the isomorphism. Now we're going to look at isomorphisms between groups. So when one group is isomorphic to another group. This is an example which is close to my heart, because when I was a kid, we used to have these things called slide rules. Now, I don't know if you've ever seen a slide rule, but they look something like this. Some of you may have seen this, some of you may not have seen it. The middle piece sort of slides in and out. The end pieces stay whatever, but the middle piece slides in and out. And that was used to make calculations. Really amazing, the calculations you can make on this. And see, that's that middle piece slides in and out. And I'm not going to get into the whole thing about slide rules. You can always go find in YouTube tutorials how to use a slide rule. You can even buy a slide rule on easily online, find one on eBay or one of these places, buy a slide rule for a few bucks. And it's kind of cool, the slide rule, but it's based on logarithms. That's the system. That's how slide rules work. So there's an isomorphism between R plus means the positive integers with multiplication and the complete integers with addition. So, and this is something until the 1970s when the price of calculators dropped. Because I remember when calculators existed. I remember, first of all, I'm very old. So I remember before calculators. And I also remember when calculators existed, but they were very super expensive. And people used slide rules. And what they would do, the way the slide rule worked, is that it created actually an isomorphism, made a rule, the translation rule, is that that's 8. This number here, 0.90309, that's log 8, base 10. And the dot, which is the multiplication, got translated into a plus and adding is easier. And here 125, that's the log of 125 base 10. If you don't believe me, let's just take a look here. Let's go to 125 and take the log, and we get 209, just like it says right here. So, and if we take 8 and we take the log, so we get the 0.902. That's where those numbers came from. And when you add them up, you get 3. But 10 to the third power is 1,000. So this tells me that 8 times 125 is equal to 1,000, and I can get it from saying. Now you may say this looks so complicated. 8 times 125 equals 1,000. It's not so hard to figure out. But if you get more complicated numbers, it actually works. Logs is an amazing system, and slide rules are amazing. Anyway, but this is like sort of an isomorphism. This is what we call an isomorphism. Let's look at it in a more general way. Let's look at the actual definition here. So the definition of an isomorphism between two groups is if you have a group called G1 and another group G2, each one has their own individual operation. Star 1 and star 2 are the operations of each group. So if I have this function, which is an isomorphism from G1 to G2, if F is a bijection. Bijection means it's 1, 1, and it's onto, meaning that every element in G1 is matched up with every element in G2. And it's 1, 1 in the sense that no element in G1 gets matched up with more than one element of G2. No element of G2 is matched up with more than one element of G1. And plus every element in G1 and G2 have a mate. So basically that's what it means when we say bijection. So it's 1, 1 on one-to-one correspondence or one-to-one onto correspondence. Anyway, if I look at a product of A star B, that's going to be equal to F of A star F of B. Now, F of AB, this is A star B, but when I'm inside here, I have to use the operation from the first group, but that'll be the same as doing a function on each individual element and then operating them in the second. And it's going to give me the same. This is the definition of an isomorphism. And basically what it means is that these two groups are isomorphic. It basically means that they're the same thing with different names. That's really another way of saying it. Okay, so so as an example, we're going to look at two different groups. The first group is just going to be, or one group is just going to be the real numbers with the operation of addition. The other group we're going to look at is the group of 2 by 2 matrices, where I have a 1, 0, and a 1 in these three positions, and I have I have a variable A. A is any real number in this top right position, and the operation is going to be matrix multiplication. And well, if I have A and B are real numbers, F of A is whereas F is going from R to G. So F is going from the real numbers to the to this group of this matrix world. So if I have a real number A, then F of A is 1A 0 1. If I have a real number B, then F of B is 1B 0 1. Well, if I do matrix multiplication, now those of you who took linear algebra, and even those of you who didn't really take a lot of linear algebra, but you've seen matrix multiplication, when you multiply these two matrices, you wind up getting A1, and then A plus B up here, a 0 and a 1. Notice that's the same thing as F of A plus B. If I take the real number A plus B and biject it or inject it, whatever you want to say, into G, I get this guy right here. So we see that when I so first of all, it's a very obvious simple one-to-one correspondence because A corresponds to 1A01. That's easily bijection. And B, we have this property that if I multiply F of A times F of B, it's the same thing as now. This is multiplying and that's adding. What's going on over here? Well, it doesn't matter because the operation in the group G is the matrix multiplication. The operation in group R is the addition. So these are just different operations. So it's all good. It's all good. That's my star 1 and my star 2, like we had in the definition. Okay, and now of course we can see a lot of other cool things here. We see that F of A times F of negative A is the same thing as F of 0. And if you do the matrix multiplication, you'll see it's going to work out. Again, if you know how to do matrix multiplication, you'll understand why this works. I'm not really going to go here teach a whole class on how to do matrix multiplication. Maybe I should a little bit. Think about that. Actually, this is how you do 2 by 2 matrix multiplication. If you have a matrix like this times a matrix like that, this is the product. And you could see that if you apply this rule to what we to the example we just did over here, it is going to work. Anyway, and I'm not going to go elaborate on that. You could take a course on linear algebra or whatever. Moving on, let's get some more insights into isomorphism and some of the properties of isomorphism. So first of all, if you have an isomorphism, so T represents an isomorphism between the group G and the group H. So it's always going to work out that the identity element from G is gonna map to the identity element of H, and the inverse of T of A is the same thing as T of A inverse. And if I have a subgroup in G, then the map of that is going to be a subgroup in H. And not only that, but K, which is my subgroup in G, will be isomorphic to H, which is the subgroup in K. And this is pretty awesome. Now, it's going to be very obvious if two groups are not isomorphic. For example, if they have different cardinalities, they're not going to be isomorphic. If one's a billion, the other one's not a billion, they're not going to be isomorphic. If G has a kind of a subgroup that H doesn't have, it won't be isomorphic. You know, there's a lot of very quick ways that we could see if two groups are not isomorphic. Here's another example of isomorphic groups. Suppose we have mod 4 multiplication, and I'm looking at the subgroup of mod 4 of just 1 and 3. And we have mod 2 addition, so mod 2, we just have 0 and 1. Well, first of all, the isomorphism is going to be 1, just match these up. 1 goes to 0, 1 goes to 0, and 3 maps to 1. So now you may say, wait a second, how is this an isomorphism? Shouldn't 1 go to 1? Why is 1 going to 0? Well, 1, let's give it another, I'm going to give it a, let's see. 1 and 0, I just got to say here is that they're each the respective identity elements, because 1 is the identity element of multiplication and 0 is the identity element of addition. So it really works out that we really do have an isomorphism here. So basically, if I'm going from, let's write it this way. So T of 1, oops. T of 1 equals 0, and T of 2, T of 3, T so T is an isomorphism from the mod 4 group to the mod 3 group. T of 1 is equal to 0 and T of 0 is equal to 1, and that does create an isomorphism between these two groups. So here is a multiplicative group, here's an additive group in different mods. Although actually it's funny thing, this group here is actually a subgroup, whatever. But the point is that it works and it's beautiful. So I'm gonna take this, I'm gonna put this in our little in our little scroll. And we'll have it for posterity. Right. And it's all beautiful. So let's just where did my thing go? Let's put it in here. And so again, these are just different examples of isomorphism. Isomorphism is pretty cool and awesome. And again, this is another, and this is also a concept. If you take linear algebra, you'll see this concept. Anyways, it's been loads of fun. Speaking of linear algebra, I just want to give a little plug. I'm teaching linear algebra class in the spring semester of 2022. That is the story with that. Anyway, that's it, everybody. It's been loads of fun, and have a lot of, as the great Galileo said, no, it was a great, well, Galileo said that mathematics is the language of the universe. And someone else, I forgot who, said, with me, everything is math. So have a very happy mathy day, and bye.